Good day everyone, my name is Karen, and I will be presenting the work titled Synthesis and Characterization of MnO, manganese oxides, thin films and their possible application in supercapacitors. The use of manganese oxide thin films in electronic devices, such as capacitors, supercapacitors, transistors, and different array circuits, have important application for energy production, as manganese oxide is an abundant and environmentally friendly material. Manganese oxide thin films were synthesized by DC Sputtering at three different powers. A structural and morphological characterization is reported, and their possible application for supercapacitors was investigated through electrical characterization. The films of around 100 nanometers were fabricated on glass and PET-E2 substrates using 30, 40, and 50 watts. The samples were characterized using X-Ray Diffraction and frequency response analysis with Bode plots. The results showed that the manganese oxide thin films grow a crystalline structure and uniform morphology. The electrical characterization indicates that depending on the characteristic of the substrates on which the manganese oxide films are deposited, application as a semiconductor for energy storage and delivery can be designed with a wide range of geometries. Overall, this study provides valuable insights into the synthesis and application of manganese oxide thin films using different substrates and the optimization of the variables used in the deposition to obtain uniform and reproducible films. The experimental procedure is the following. First, we use a substrate cleaning with xylene, acetone, and propanol, and it was dried with a nitrogen gun. Then the sputtering on the manganese, which we will later see that is manganese oxide, MnO, and we use the optimization of the parameters for 30, 40, and 50 watts. Then an X-ray diffraction characterization is done, and then the electrical characterization with the frequency response analysis is done. Results and discussion. The X-ray diffraction patterns for the glass substrate sampler corresponding to the MnO phase. The references are specified by this chart here mentioned, and at 30 and 40 watts the 2-to-1 plane can be identified, but is lost at 50 watts. Unfortunately, for the X-ray diffraction patterns of the PET-E2 substrate, the signal is lost because of the PET-E2. We only see the peak of the PET. For a further analysis, it took right aggressive incident X-ray diffraction, where we could observe the peaks of the manganese layer. Following the characterization, we have the frequency response analysis. The frequency response analysis is done with a 5-volt sinusoidal signal, and the surface of the film is used as a device under test, here shown in the image. This technique allows us to understand the electrical behavior at different frequencies throughout both plots. With these plots, we are able to determine if there is a gain or attenuation of the signal, and if there are inductive or capacitive effects in the film with phase shifts. For the glass manganese oxide samples, these samples exhibit attenuation of the signal. At 50 watts, the attenuation is of minus 16 decibels at 100 Hz. This sample is one of the presents more losses, while at 40 watts is the one with less attenuation, with minus 4 decibels at 100 Hz. The 50 watt sample shows more capacitive and inductive effects. Now for the PET-E2 manganese oxide, we can see that the attenuation is severe and is close to minus 110 decibels. The phase displacement is related to capacitive and inductive effects, but we can see that it is also affected by this loss of the signal, so it is not very conductive. For the conclusions, we have that the manganese samples were deposited on glass and PET-E2 substrate at 30, 40, and 50 watts with this sputtering in an argon atmosphere. The layer is identified through X-ray diffraction as manganese oxide on the glass substrate, and the 111 plane is identified as predominant in the three powers used. The manganese oxide signal is not shown in the X-ray diffraction patterns of the PET-E2 samples, as the PET is the most intense signal. For the frequency response analysis on glass, the manganese oxide sample at 40 watts is the one that presents less signal attenuation from 100 Hz to 10 MHz, but the 50 watts layer have the most capacitive and inductive effects, which are of interest for solid-state supercapacitors. Finally, we present the authors of this work, and thank you so much for your attention.